This is where we left off. We were talking about ether reactions, and we were talking about the mechanisms and the protonation step and the carbocation stability and cleaving the ether off in order to make these two products. And in the last reaction, we made two products. We made this product, which was the halogenated compound. And then if you notice, we also made an alcohol. So this alcohol did get generated in the product side because the ether cuts in half, and this was the other half of that ether group. So I'm always going to get an alcohol, and I'm always going to get a halogen because of this. The other thing I want to tell you is that you are getting products, and these products are partly alcohols as well. Now, this is going to cause us a little issue later down the road, and I'll address that, maybe if not in this video, in the next one at least. But this is a product, it is an alcohol, and these alcohols can also undergo reactions. And if I'm taking these ethers and I'm reacting acids in them, and I'm getting alcohols as a product, folks, I got to be careful, because these alcohols can also react with the acids that's intended for the ethers in the reaction. So how do we prevent this? What goes on? Is this something that we need to keep in mind? How do we handle it and clean it up as these reactions go forward? So before we talk about any of that mess, I want to do another example, another curvy arrow mechanism. So let's look at CH3, O, CH2, CH2, CH3, and this time let's just add an acid. I don't know, HBr. We used HI last time, so we use HBr this time. So the directions are going to say, show the curvy arrow mechanism of how these two things react and what kind of products get formed. Okay, so this oxygen's got some free sets of electrons. I can draw those on there. The bromine has some free sets of electrons. I can draw those on there as well. So there they are. And now these two things need to come together. They need to react. How do they do that? Well, HBr is a proton donor. The reason is because bromine's electronegative somewhat. It's over on the side of the fluorine on the periodic table. That bromine is going to suck up electrons, and if it can suck up electrons from the H to Br bond, then this is going to donate and kick off the hydrogen, and bromine's going to be left with those extra electrons, and bromine can easily handle them without a problem. All right, so there is our acid. That's our proton donor. That will eventually look for a home. I mean, you're going to get ready to kick off hydrogen into the street. Hydrogen has to have somewhere to live. It can't just float out there on its own forever. So it's got to go somewhere. And that's the purpose of the oxygen. So this oxygen's negative, partially negative. It's got some electrons there. This negative source goes to the hydrogen, pink, and off it goes. So, hey, hydrogen, you're in a relationship. That's an HBr. Bromine's not doing anything for you. The only thing that bromine wants is want, and I know you're not happy. So why don't you just come over, hang out for a little bit, and we'll see if we can get this to work between you and me. And that hydrogen says, okay, I'll go, and away it goes. All right, so now we've got these electrons between the H and the Br. So those electrons are going to go to that Br because that's what bromine wanted anyway. Not a problem. Bromine can handle them. It's got the extra room. Again, it's a big boy. It's a big girl. It can take care of itself. Mr. and Mrs. Independent right there. So when this happens, in the middle, right, this is not our product, but this is kind of in the middle stages, we see this CH3O, and then CH2, CH2, CH3, and this oxygen now has brought in a hydrogen, and this oxygen is now positive. Again, I told you it happens every single time. That's what goes on. Oxygen has bit off more than what they could chew. 3 bonds, 3 relationships. It's not going to work. Oxygen only needs 2. Oxygen wants to see 2 people at the same time all the time. So the oxygen's going to have to make a decision, just like it did before, on which one of these bonds gets cleaved. Well, if I take a look at the oxygen here, this oxygen has just brought on a hydrogen. It's going to keep that hydrogen around. Why? Because it can have its way. That oxygen knows that that hydrogen is not going to put up a fight. It's disposable. Oxygen calls the shots. Hydrogen listens every time. So it's going to prefer that hydrogen stays there. So the choice here, just like last time, is between the two carbons. Which one of these bonds will I cleave in order for this product to form? Because that oxygen is going to have to make that decision. It can't have these three bonds like this. Two, that's all it needs. That's all it wants. It's got to get rid of that positive charge. But this is the protonation step. This is how the ethers have become activated. So over on the left-hand side, if we cleave the left bond, this is a primary, basically, carbon. And then over here on this side, this carbon is also a primary carbon because it's attached to only one other. So now you're going to go back to this one and you're going to go, well, wait a minute, this carbon really isn't attached to anything else. No, it's not. It's just one carbon and that's it. So this is really what we would call a methyl cation. A methyl cation and a primary cation are going to be compared. Out of the two, the primary cation and the methyl cation are pretty much equal as far as being unstable. Neither one of those want to form. Neither one of them. So this carbon on the left is going to put up a fight. And it's going to go, if you leave me, this is not over. And then this carbon over here is going to say, oh, absolutely not. If you break up with me, I will come to your workplace and I will key your car and flatten your tires and I will make your life a living, well, you know what. So oxygen's now in a bind. And oxygen's going to go, okay, what am I supposed to do? I've got these two carbons. They're pretty much equal as far as unstable. I don't want both of them to go crazy. No matter which one I break up with, they're threatening my life. So how am I going to fix this problem? So oxygen calls up the friend. And oxygen says, hey, buddy, listen, you know, I need to break up with one of these. And I think that this is going to be much easier if you come and help me out. So what I want you to do, I want you to come over and I want you to meet one of these people that I'm dating. And I want you to kind of start making the moves on them. Because if you do, they might get distracted and they might pay more attention to you and like you better than what they like me. So bromine takes the phone call. And bromine says, okay, yeah, I'm not doing anything else. I mean, I'm fully negative. That's a positive piece. So this bromine is on its way over to the house, and it comes in, and it says, okay, which one do you want me to basically distract? And oxygen says, well, right now, this carbon over here, this carbon that I'm dating has got some friends over. So I think that you might be having a little bit easier time to distract the one to my left. And that's because that carbon is not really surrounded by friends. It's the less sterically hindered one. It's steric hindrance. That's what drives this decision. So bromine says, okay, not a problem. You know, over here by himself, I can distract that. Not a big issue. And then you can break up with them and then go off on do whatever you want to do. So this bromine's going to come in, and this bromine is going to attack that carbon. The reason is this oxygen's an electron sucker, and it wants these electrons that it can break up with. So this is going to cleave. That oxygen's electronegative. It sucks the electrons from the bond, and off it goes to make an alcohol. All at the same time that this bromine comes in, and that bromine distracts that less sterically hindered carbon. So the products that we have here, when these two things are unstable or when they become a tie, is that the halogen will be added on to the least sterically hindered piece. And then that allows the alcohol to be formed, CH3, CH2, CH2, and OH. I just wrote it backward. Hopefully you're okay with that. It means the same thing. But those are the two products that I have. Now, the difference here in the mechanism. These are pretty unstable on both sides. They're not going to be wanting left alone. Primary does not undergo SN1 reactions. That's the mechanism that we did before, because we had that tertiary carbocation. That was stable. These primaries are not. The methyls are not. So this cannot undergo a SN1. This one cannot undergo an SN1. And if you look at the mechanism here, this is a full-blown SN2 mechanism. That means two things are happening at one time. The C to O bond is getting broken at the same time that bromine is coming in to distract. A full-blown carbocation is not formed, and the reason is because primaries and methyls cannot form full-blown carbocations very reliably. They are so unstable, they do not want to do them. So this is a different type of mechanism. SN2s and SN1s happen in ethers. SN1s happen in ethers when they can leave behind a stable carbocation. SN2s happen in ethers when they cannot. So there is a difference between the ether mechanisms. Now, out of these two, SN1 is going to be preferred. When it can happen, that's the one that's going to be preferred over the SN2s. So, let's kind of sum up some of the things that we've talked about so far. Number one, we always look for the more stable carbocation. That oxygen is going to leave behind the more stable carbocation when it can happen. Number two, carbocation shifts in those reactions, they can happen. But keep in mind that if you've got tertiaries that are left behind, folks, those tertiaries are not going to move, right? I mean, it's very hard for them to move. Only a couple of things beat out a tertiary carbocation as far as stability goes. That was a Chemistry 251 topic. So we're going to say look for carbocation shifts, but keep in mind these will rarely happen anyway. So if you forget to do this, it's probably not a big deal on your end. Next, number three, the halogen is then going to attach to that more stable carbocation. And this is what happened in our first example. So this is representative of a SN1, and this is the preferred method that ethers follow. Carbocation forms, carbocation accepts the halogen, two pieces get added on or formed, an alcohol and a halogen. The other carbocations that are out there that undergo an SN2, like our second mechanism example, these are going to be your methyl carbocations, your primary carbocations, your vinyl carbocations, which was a carbon double bonded to a carbon that had a positive charge on it. That was a Chemistry 251 topic as well. An aryl. What was an aryl? This was a ring structure that had an alternating double, single, double, single, double around it. And that is a carbocation that's attached to one of those carbons. That's also not going to fly. That's also very unstable. It disrupts everything in that ring. So anytime we get these carbocations, the SN2 route is going to happen, and that SN2 route is where we needed to start looking for less sterically hindered pieces. But these ethers will prefer to break at the site that leaves behind the most stable carbocation when they can form. Okay, So what other reagents will get these ethers to cleave? I mean, is HBr and HI really the only ones? Well, if you looked at the protonation of alcohols, think about those. What other reagents did we use? We used things like SOCl2. That's thionyl chloride. And then we use things like PX3, so PBr3, PCl3, right? PI3. And then we used like tosyl chloride stuff, sulfonate esters. Tosyl chlorides went in, protonated the alcohols, and away they went. The problem here is that none of these react with ethers. None of them. Ethers generate alcohols. Remember, I mentioned that just a few minutes ago. They make alcohols as products, and the alcohols will begin to react with these reagents. And then all of a sudden, it prevents the ether reaction from happening. So these reagents especially are very sensitive to those alcohols. And as they are getting generated on the product side, those products are now eating away the reagents that are intended for the ethers. And because of that, these do not react very well with ethers at all. There's almost no reactivity with them. So thionyl chlorides, these phosphorus trihalides, and the sulfonate esters like the tosyl chlorides that begin to go on, these are a no-no in the ether world. Which means good news for you. And what is that good news? The good news is that it's really just HBr and HI reactions that we have to worry with when it comes to ethers. That's right. That's it. So even though this is a different functional group, it really plays off the same mechanism that alcohols do. And we use some of the same reagents that alcohols use. And not only that, but the only reagents that we have to focus on here are the acids, HBr and HI, and that's it. So we're going to say that ethers have a very strong tendency to not react with hardly anything at all. They're very, very stubborn. And it's for these reasons. Now, because they don't react very often with pretty much anything, that also makes them extremely good solvents. It's not uncommon if you are in a laboratory and you're doing a reaction and a ether has been chosen to be a solvent. And this is why. They are so reliable to stay as an ether, unless we're adding HBr and HI, but they're so reliable to being stayed as an ether that we can feel pretty good about adding those into a solution as a liquid solvent and allowing a reaction to go forward, knowing that the ether is not going to take part in the reaction. Now, what are some of these common solvents that you might see in a laboratory? Well, here is the assortment of some of the most common that are out there. So one of the most common and simplest really is this thing called diethyl ether. And instead of saying diethyl ether, then we're just going to shorthand this to ether. We saw this in Chemistry 251. Diethyl, well, there's an ethyl group here to the left and an ethyl group there to the right. So that's why we call this diethyl with the word ether on it. All right, so diethyl ether, very, very common. We call this ether for short, and people know exactly what you're talking about. If I don't want to use common names, how do we IUPAC it? Remember, I told you I'll do some nomenclature review. Well, you find the longest carbon chain, and no matter which side you start on, it's going to be 2, so this is going to be called an ethane. And then the other side, well, this is the first carbon, that's the second carbon of the long chain, because this one, we start with number 1, because that's where the group's attached. And this is a 2-carbon chain, F, and the O stands for oxy. So this is going to be called a ethoxy ethane. just a review. This ether is also very explosive. That's the problem with some of the ethers. Over time, they build up peroxides. And these peroxides begin to build up in the container, and those peroxides are very explosive to the point that you have to hire bomb squads to come in and remove the ether away. So the issue here, ether is a very good solvent. Ether is very commonly used. The problem, if you don't use it quick enough, it begins to build up peroxides, and then the jug can go boom. Don't want that to happen in a lab, do you? You don't want to be calling bomb squads around to take off ethers out of your lab just because you were a little lazy on checking it and dumping it when it was supposed to be disposed of. Another ether, tetrahydrofuran. I like to call this the cupcake molecule. And the reason I call this the cupcake molecule is because here's the ring with that oxygen on top, and it looks like a little cupcake with a cherry on top. All right, so there is your cupcake molecule of tetrahydrofuran, and that is abbreviated as THF. Notice that is a ROR. We also have an extension of that ring. Instead of a 5-membered ring, we can do a 6-membered ring with the oxygen on one of the joints, and that is called tetrahydropyran. Well, if we can do oxygen on one of the joints here, we can also do oxygen on one of the joints directly across from it. And we can call this 1,4-dioxane. This is a very, very potent substance. Very hazardous. Very toxic. You talk about suit and gloves, 1,4-dioxane. That's one of those that you want to pay special attention to. It also leads to other things that are pretty nasty as well. Okay, well, here's another ether. This is an ROR, right? There's our first ether group, and here's another ROR. So this one is 2 ethers in the structure. So the name of this one, dimethoxyethane. Okay, well, why do they do that? You look for the longest carbon chain. That longest carbon chain is right here. That's 2 carbons, so that's where the ethane comes from. And on carbon number 1 and on carbon number 2, you have the same type of group, and that group is an OCH3. So that first carbon is a meth, and then you add on oxy for the O, and this is called methoxy. So there's the methoxy. You have 2 of these groups, don't you? One on the first carbon and one on that second carbon, so that's why they use the word di, and we have to tell you where they're located. So on spot 1, I have a methoxy, and on spot 2, I have a methoxy. So 1,2-dimethoxyethane, and that's abbreviated as DME. Finally, the last one, it's a pretty common ether. This is our tert-butyl methyl ether, and this is MTBE. Again, we've already used this one. We did this in our mechanism in that very first example that we did. Now, they've shorthanded this. So up here, I'm just going to fully draw it out. So this is a CH3 group onto an oxygen, onto a carbon, and that carbon has 3 methyl groups. So one up here, and one to the side, and one down below. So there is our tert-butyl group and our methyl group. That's what we used in our very first mechanism example. Again, tert-butyl methyl ether, that is the common name. And in the abbreviation, notice they switch the alphabetizing and they put MTBE because it looks a little bit better. What else about ethers do I want to tell you about? Well, the other thing about ethers is that they are very common anesthetics. They're common anesthetics because, number one, they're pretty stable as far as reactions go. They don't really react with anything hardly at all. And diethyl ether, the stuff that I told you could build up peroxides and explode if you're not careful, was one of the first anesthesias that was out there. So down here at the very bottom, I don't think this guy has an anesthesia, right? I mean, look at his face. Look at all the people that are basically around him trying to saw off a leg. I mean, if you ask me, this is like a horror movie, okay? I mean, come on now, folks. Why on earth do you want to surround that poor man? And what's he doing? I mean, is he opening up his eyes just so we can get a better look? That's kind of creepy in itself, right? And then look at this guy. I mean, he definitely looks like he belongs in a horror movie. So before anesthesia came along, you could imagine things like amputation. How on earth do you do this to someone while they're wide awake and you want to saw off a leg, maybe due to an infection or whatever the case was? You can imagine the horrors that people had to go through before anesthesia made its way into the medical world. So diethyl ether was one of the first. So up here, you're actually seeing an illustration of the first usage of diethyl ether to a crowd of physicians and medical students, showing that they can give you diethyl ether or ether. It will make you pass out. You will not feel a thing. And then they can go through and do whatever kind of surgery that they need to do on you. So this was the very first encounter of a very early anesthesia. Now, the problem here is that anesthesia, when you wake up from it with ether, has tremendous, horrible side effects. I mean, you talk about nausea, vomiting, sick at your stomach, headaches, cramps. All of these things are going to come along with diethyl ether. So there had to be anesthesia out there, and those anesthesias, well, they're probably going to be a little bit better than diethyl ether. However, diethyl ether is going to still be pretty much the safest choice out of all the other anesthesias that are on the market. Now, it has been replaced. This is the whole medical training for anesthesiology, and they basically teach you how to use the anesthesia the proper way so you don't kill somebody with the anesthesia. So some of these others that you might see are compounds called isoflurane and sodium pentothal or pentothal. All right, so these have issues though. And the issues here is that something like the sodium pentothal, ED, this ED means effective dose, not erectile dysfunction. Okay, so effective dose. So the effective dose of that compound is the concentration that's needed in order for it to work. And if you look at the effective dose, the ED, and you compare it to the lethal dose, and that lethal dose is LD. If you compare the ED to the LD, you're at 75%, which means you only have a 25% wiggle room before you give that patient too much anesthesia and it kills them. That is the problem with some of the anesthesia that is out there on the market. However, other things that came along a little bit better, and these are things like propofol that killed Mr. Michael Jackson. Propofol can be mishandled. It can still kill people. However, propofol is a safer anesthesia than some of the others that are on the market. And when you wake up from that anesthesia, there's very little side effects that happen after you come to your senses. So here are some of the structures of these common anesthesias. And if you look, here's the structure for ether. It is a ether group. Here's isoflurane. That is also an ether group. Here's enflurane, which is a modification. It is another ether group. Here's halothane, but halothane is not an ether. However, it is halogenated, and it does kind of the same job that some of these ethers did back in the past. And then here's sodium pentothal or pentothal, and here's propofol. Notice that these two structures, they are not ethers at all. There's no ether functional group in there. I don't see one. Do you see one? I hope not. There are other functional groups that do the same thing. However, ether was really the one that kind of struck this whole medical science field into existence. So you can thank ether for that very, very early on. Just don't take a big sniff of an ether bottle and make yourself pass out, and you'll wake up and you'll feel miserable. You'll feel worse after the fact than you did before the fact. And in addition to that, all of these movies that they dab stuff onto a rag and they put it over your nose and then within a couple of seconds, those people get passed out. No, it doesn't happen that fast. All of that is for movies. So all of that is fake, 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 fake. All right. So here's an example. This is where I'm going to stop the video. I would like for you to take a stab. Kind of take what you've learned in the last video or two and see if you can come up with the proper products for these reactions. So the example problem says, what products are formed if the following ethers react with HI. So we have A, B, C, D, E, F. All of these have ether groups. So you're going to have to figure out, okay, we're going to protonate it. And I know we're going to protonate it because we're using HI as the reagent. So when that protonates, where does the oxygen break? Does it break to the left or does it break to the right? And you're going to have to look at things like carbocation stability in order to make these decisions. And then if it's a tie, then we look at things like sterically hindered groups. So good luck. Try them, please, please. And if you get the wrong answers, again, when we explain each one of these, you might realize why you made your decision in the first place and know that at that point, it's the wrong decision to make. I think this is a better way to learn organic sometimes. So see what you can come up with. Break these ethers apart into two fragments, make one an alcohol, make one a halogen, and see if your answers match mine in the next video.